Hello, and we're looking at Chapter 3B, Measurements. Are there limits in measuring? Actually, yes. Anytime we measure something, whether it's time, length, mass, there's always going to be some uncertainty. That's just the reality of it. We can't get it down to the perfect thing. So the question is how accurate is the measurement or a measuring instrument? And of course, you have to ask another question. How close is the measured value to the actual or accepted value of what is measured? Now, one way we get to deal with something like this is something called percent error. So what is percent error? Well, there's a couple of things involved with it. You have, there we go. You have an observed value, which is what you have, what you measured, and an accepted value. So we would do a few examples in class over something like this, because this is something that we can do in our lab experiments. So you have an observed value, what you physically measured, and they have the accepted value is what is generally known to be as close as we can get to it. So observed minus the accepted, and notice the absolute value bars there. Okay, so it's going to be a positive number, and it's going to be divided by the accepted value times 100%. Okay, so we'll do a few examples in class, and then we'll move on. Okay, accuracy. So how close a measurement is to the exact value. And if you think about it, you can look at the villain's accuracy against the hero in the movie, where the hero gets shot in the shoulder and that's it. The bullets are all over the place. Whereas the hero's accuracy against the villain in the movie, you know, not much you can say about that now, can you? No, you can't. But then, of course, that also involves the question of precision. Okay, so it indicates how repeatable a measurement is and how exactly one can make a measurement. Okay, so precision is an important thing. How close can you make the measurement? How repeatable is this? You could be precise in your measurements and be totally off on the real answer. Now, measurements have limited precision. This is why we have uncertainty. Now, here we have three pieces of equipment that we use in terms of measuring mass. So a triple beam balance would be like 0.1 gram. The analytical balance on the right here is 0.0001 gram, or 1/10,000th of a gram. And then we have the electronic balance that we use in class in our lab is 0.01 gram. So they have limited precision depending on what is needed. So what about precise versus accurate? Well, bullseye targets give us the pretty good idea of what's happening. You can have high precision, high accuracy. Notice where the bullets are all pretty clustered together. Then you have low precision, high accuracy. You'd say, but wait a minute. Well, if you look at the accuracy there, the bullet holes are fairly close to our target center, but they're kind of scattered, so the precision is off. Now, you can have high precision, low accuracy, if you notice where the holes are grouped in one area, but they're off the target center. Low precision, low accuracy. Again, you don't have a tight grouping of holes, and you're not even, one is close to the center, maybe two, but the rest are scattered. It doesn't work. Real life example, think about sighting a scope on a shooting range. You always take the time to go and make the adjustments in order that you get high precision, high accuracy. So moving away from precision and accuracy, we got to look a bit at integrity. So that's required when reporting measurements. If you're way too precise for what you are, then you'd be considered dishonest. If it's too little precision, it's considered to be sloppy. Now, why is this important? Well, First off, integrity with yourself, okay, colleagues and God. Now, what do we mean by integrity? How about being honest when nobody is looking, okay, when nobody's checking up on you? That, to me, would be integrity. Scientists may question the validity, the truthfulness of the data. That's one of the reasons why reporting measurements and you're doing it where it's the right precision, okay, that would be important. So now it gets us into significant digits, SDs. Report measurements to 1/10 of the smallest decimal increment. Okay. The purpose. SDs determine the important digits you need to write down, to record. It also indicates how precise is the measurement. How far do we go with it? I'm just going to go through here. The significant digits, or sig figs, I like to call them that, apply only to measure data. They do not apply to counted or pure numbers. So like example 100, 1 double, 3.14, you don't have units, we don't care. Okay. Significant digits do not apply to ratios that are exactly 1 by definition. So 60 seconds to a minute, it doesn't matter because it's a conversion factor. They are equal to each other, 12 inches to the foot, 1,000 grams to a kilogram. Doesn't matter. Significant figures do not apply, or significant digits. All non-zero digits are significant. So 25.4 is 3 SDs. 13.78 is 4 SDs, and then of course that giant number, I'm going to leave that one up to you to count. Now, rule number 3, all zeros between non-zero digits are significant. So that 100.5 Celsius, you got 4 significant figures. 1.09 is 3 significant figures, and that giant long number there, I'm going to let you count that out. Number 4, the decimal point defines if the zeros are significant. Okay? So if a decimal point is present, all zeros to the right of the last non-zero digit are considered significant. So 20.0 seconds, it's 3 SDs. You'd say, but wait a minute. You could just say 20 seconds and that's it. What's the difference between 20 seconds and 20.0 seconds? It's how far do you carry out your measurement? How do you deal with the precision? Okay, I'm measuring it by 1/10 of a second. Yep, I got 20 seconds and I got 20.0 seconds. Same value, but the 20.0 seconds is more precise of a measurement. Okay? And then 250.00 liters, that's 5 significant digits. Now, if a decimal point is not present, then no trailing zeros are significant. So 2,500 milliliters, it's just 2 SDs and that's it. Okay? In decimal numbers, all zeros to the left of the first non-zero digit are not significant. So 0.075 is 2 SDs. 0.0010 seconds, it's 2 SDs. It's the one with the 0 following after it. Okay? 5. Significant zeros in the ones place are followed by a decimal point. Okay? So, putting in the decimal there makes the difference between 2 significant figures and 4 significant figures. Again, this is a question of precision. That's the whole point about measurement. Because remember, we always have uncertainty. SD Rule 6, the decimal factor of a significant digit, the decimal factor of scientific notation contains only significant digits. 2.5 times 10 to the third, that's 3 SDs. The 2, the 5, and the 0. And with that, we are done here for dealing with measurements and uncertainty in measurements.